Hello all, I'm Dr. Karthika of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about interaction of radiation with matter in medical physics. First of all, what do you mean by ionizing radiation? We know that ionizing radiation is a radiation that has sufficient energy to remove electrons from atoms and it creates ions. This ionizing radiation, we can have two classifications. One is photons and another one is particles. In photons, we have gamma and X-rays, and particles we have alpha, beta and neutrons. Okay, next we see the basic concepts of interaction of photons with matter. See this one. In this, we have three possible occurrences when X or gamma photons in the primary beam pass through the matter, any matter or any object. First one, there is no interaction. It is called transmission. Second one is absorption and the third one is scatter. Okay. Later two are methods of attenuation, and next we'll see the example for attenuation. See this one. This figure, it clearly shows the attenuation of an X-ray photon. See this one. First, the incident monoenergetic photons are entered into the matter or any object. We can consider any object. And in the another side we have detector. Okay. First one, 1000 photons are entered into the any object or matter, and at last it was 62.5 photons. While transmitting photons, it was 1000. While it reaches the end, it was finally 62.5 photons. This shows how the attenuation takes place in a monoenergetic beam. Okay. Next one, the three main interactions of X and gamma rays with matter. Okay, the first one is photoelectric effect. It is very important in diagnostic radiology. And the second one is Compton scatter. It is also very important in diagnostic radiology. And the third one is the most important thing, power production. It is very important in therapeutic as well as diagnostic radiology. Okay, then what do you mean by photoelectric effect? Do you have any idea about it? Okay, here it will be the answer. Here, all of the energy of the incoming photon is totally transferred to the atom, and the following interaction, the photon ceases to exist. In this, the incoming photon interacts with an orbital electron in an inner shell. Usually we represent in terms of K, kernel. The orbital electron is dislodged. They dislodge the electron. To dislodge this electron, this particular electron, the energy of the incoming photon, it must be equal to or greater than the electron's energy. Okay. And also one more thing, in this photoelectric effect, the incoming photon gives up all its energy and it ceases to exist. The ejected electron is now called as photoelectron. This photoelectron now contains the energy of the incoming photon minus the binding energy of the particular electron shell. Thus, photoelectron can interact with the other atoms until all its energy is spent. Okay. And a vacancy now exists in the inner shell. To fill up this gap, an electron from an outer shell drops down to fill the gap. Once the gap is filled, the electron releases its energy in the form of a characteristic photon. This process continues and until the atom is stable. This characteristic photon produces relatively low energies and it is generally absorbed in tissues. Okay, see, this is a very clear example for photoelectric absorption. See this one. First circle, it indicates the 100 kilo electrovolt incident photon, and second one is it shows how it will be transferred. It shows the binding energy, and here we classify the characteristic X-rays A, B, C, And the byproducts of a photoelectric effect, we know that we have photoelectrons and characteristics photons. And what does this all mean? The bones are more likely to absorb radiation. We know that higher is it. This is why they appear white on the film. Soft tissue, it allows more radiation to pass through than bone. Lower is it. These structures will appear black on the film when air containing structures allow more radiation to pass through. Okay. Next one is Compton scattering. An incoming photon is partially absorbed in an outer shell electron. Here the electron absorbs enough energy to break the binding energy and is ejected. Here the ejected electron is now a Compton electron, and not much energy is needed to eject an electron from an outer shell. The incoming photon continues on a different path with less energy as scattered radiation. Okay, and this example, it shows clearly about Compton scattering. See this one, this figure. In this figure, valence electrons and Compton electrons are clearly indicated. See how incident photon affect the valence electrons, and the theta, it shows the angle of deflection, and the ESC, it is called as scattered photon. Here lambda 1 is should be less than lambda 2. Okay, the next one is pair production. Okay, in this pair production, we have an incoming photon of 1.02 mega electron volt or greater interacts with the nucleus of an atom. The incoming photon disappears. The transformation of energy results in the form of two particles. Okay, first one is negatron, second one is positron. At a negatron, it possesses negative charge, and positron, it possesses positive charge. See this one for pair production example, how incident photon gives negatron and positron. Okay, in this figure, it clearly indicates the free electrons annihilation reaction, and as well as it shows the incoming incident photon and the produced negatron and positron. Okay, next one, it is about positrons. And these positrons, it considered antimatter, do not exist freely in nature. When an electron and the positron destroy each other during interaction, it is known as annihilation reaction. Okay, next one, it is about the produced gamma photons. It may interact with the matter through pair production or Compton scatter depending upon the application. Here the pair production is used for positron emission tomography and nuclear medicine imaging procedure. It is also used in radiation therapy. Okay, while coming into pair production probability, it increases the increasing photon energy, and also it increases the atomic number approximately as z square. Okay, see this one for example. And while coming into particle interactions, we have excitation, ionization and radiative losses. Okay, in charged particle tracks, ionization track is sparse and non-uniform. We know that. Here the path length is actual distance particle travels. Here the range is actual depth of penetration in the matter. Okay, see this one for path length versus a range. Path, it always should be greater than a range. For critical applications, while path equal to range, it is normally used for low energy simple applications. Okay, next we'll discuss about the very important thing, linear energy transfer. We know that amount of energy deposited per unit path length is called linear energy transfer. In this we have high LET radiations, alpha particles, protons, etc. Okay, it is expressed in terms of electron volt per centimeter. Okay, while talking about low LET radiations, it includes electrons, gamma and X-rays. Okay, please be consider for high LET radiations we have alpha, protons, etc. And for low LET we have electrons, gamma and X-rays. Okay, and the next one is specific ionization. Number of primary and secondary ion pairs produced per unit length of charged particles path is called specific ionization. It is expressed in ion pairs IP per millimeter. It increases with electrical charge of particle. It decreases with increased incident particle velocity. Okay, the next main thing is bremsstrahlung. It is also called as radioactive losses. Here the probability of bremsstrahlung production per atom is proportional to the square of Z of the absorber. Here the energy emission through bremsstrahlung varies inversely with the square of the mass of the incident particle Z by m the whole power 2. Here, the protons and alpha particles produce less than 1 millionth the amount of bremsstrahlung radiation as electrons of the same energy. Okay, here the bremsstrahlung concept, it clearly shows the radioactive losses while interaction of X and gamma radiation with matter. Thank you.